differential equation and Legendre differential equations. For that, we will begin with a differential equation which is called as associated Legendre differential equation. Now some of you might be knowing this differential equation earlier, so let's write the form of this equation as earlier. Okay, now the associated Legendre differential equation, associated Legendre differential equation is, okay, can anyone tell me? This is 1 minus x square into the bracket d square y upon dx square. This is my first term, minus twice x into dy by dx. This is the second term, and last term is this n into n plus 1 minus this m square upon 1 minus x square. Okay, this bracket complete into y is equal to 0. Call this to be equation as 1. Okay, remember what is the difference between this associated Legendre differential equation and the Legendre differential, ordinary or normal ordinary Legendre differential equation. What is the difference is this term. So this term actually comes from when we separate this Helmholtz equation in the spherical polar coordinate system. While separating this r part from this theta and phi part, we have to get this constant minus n into n plus 1, and adjusting this constant in this differential equation, it comes here. So this n into n minus 1 is the different than what we get in a normal Legendre differential equation. So normal or ordinary Legendre differential equation is 1 minus x square into d square y upon dx square minus twice x into dy by dx minus m square upon 1 minus x square into y is equal to 0. So that n into n minus 1 is not there, and that's why this is called as associated Legendre differential equation. Try to understand the difference between normal or ordinary Legendre differential equation which doesn't contain this term n into n minus 1. This is actually a separation constant. When we go for separation of variables, that is the separation of Helmholtz equation in case of spherical polar coordinate system, we come across this type of constant n into n plus 1, and taking this constant in this equation becomes associated Legendre differential equation. So try to find out its origin. म्हणून त्या differential equationचा origin कुठं असेल तो पहा. तो एकदा origin आपल्याला कळला की it is not at all difficult to get things about this. Now we have to get the solution of this. Okay, now we are just direct the solution. The solution of above equation is called associated Legendre polynomial. Associated Legendre polynomial, and is defined as okay. Now see the symbol. This is given by PLM of x, defined by PLM of x, and this is given by, okay, it is given by 1 minus x square that raised to m by 2 into, this is the mth differentiation, d raised to m upon dx raised to m of Pn of x. Okay, so it is very easy to understand what this particular statement is. That means if I know this Pn of x, operating this operator, now this operating this operator, I get Pn this PL. Okay, I am just operating this. Okay, let's write this n, not L, it is n because we are using n there. Pnm is equal to 1 minus x square raised to m by 2 into d raised to m upon dx raised to m of Pn of x. That means getting this operating this operator on this Pn of x, I get Pn m of x. So this is my ordinary Legendre polynomial. and this is the associated Legendre polynomial. Associated Legendre polynomial. So once I know this Legendre differential equation and its solution, that is Legendre polynomial, I can get associated Legendre differential equation and associated Legendre polynomial just by operating this operator 1 minus x square raised to m by 2 d raised to m upon dx raised to m. Okay, this is to be operated on this Pn of x. So operating this operator on this Pn of x, we get associated Legendre polynomials, that is Pnm of x. So this is the definition. Whether this is correct or not, whether this is solution of this differential equation, this can be tested, this can be done. There are several books which are giving solution, or which are giving or using this method of separation or method of series solution, power series solution, and we get series solution of this differential equation is given by Pn of m of x is equal to 1 minus x square that raised to m by 2 into d raised to m upon dx raised to m into Pn of x. So getting this solution by series solution method is different thing, which we are not doing here. We are just knowing that if I know Pn of x, I can find out Pnm of x. So from associated ordinary Legendre polynomials, how to obtain this associated Legendre polynomials, and for that case we have to operate this operator 1 minus x square raised to m minus 2 m upon 2 and d raised to m upon d raised to xm dx raised to m. Operating this operator or this, I can get this particular associated Legendre polynomial and all these things. Okay, so this is how this thing one is to be known, one is to be understood. Similarly, there is another method, just like Legendre and other types of special functions. There can be a Rodrigues formula. The associated Legendre polynomials, associated Legendre polynomials can also be obtained by, this is one method, second is obtained by, okay, using Rodrigues formula, DRIGUES, Rodrigues formula. So just remember its formula. The Rodrigues formula is given by Pnm of x is equal to associated Legendre polynomial is given by 1 minus x raised to 2 x square that raised to m upon 2. Now it is d raised to m or not this, okay, it is to be 1 upon 2 raised to n into n factorial multiplied by dm raised to m plus n divided by dx raised to m plus n into x square minus 1 that raised to n. Okay, now try to understand the difference between Rodrigues formula for ordinary Legendre polynomial and Rodrigues formula for associated Legendre polynomial. So if you remember, this is given by Rodrigues formula for this Pn of x. Okay, of comparison, this is given by 1 upon 2 raised to n into n factorial raised to d raised to n upon dx raised to n into x square minus 1 that raised to n. So using this formula, I can get ordinary Legendre polynomials, and using this Rodrigues formula, I get this associated Legendre polynomial. So difference here is 1 minus x square raised to m by 2. This additional component is here, and this d 1 upon 2 raised to n into n factorial is same. Here the differential was d raised to n divided by dx raised to n. This time it is d raised to m plus n divided by d raised to x dx raised to m plus n, and otherwise all the formula for this Pn of x, Rodrigues formula for Pn of m n of x, and Rodrigues formula for this Pn of x, these are just same. So for not same, but the form of that particular formula is same. So we can find out, or we can operate this particular things there, and we can get such type of associated Legendre polynomials very easily. Okay, can we obtain one or two? So let's try using this. Put n is equal to 0 and n is equal to 0. Okay. N is equal to 0 as well as m is equal to 0. So I'll get P0 of x is equal to 1 minus x square raised to 0 upon 2 into 1 upon 2 raised to 0 into 0 factorial multiplied by d raised to 0 plus 0 upon dx raised to 0 plus 0 into x square minus 1 raised to 0. So everything here, this will be 1, this everything is 1, this is also 1, and x square minus 1 is okay raised to 0, whatever it is, so this is also going to be 1. So this is 1. So that's what I will get. P00 of x is equal to simply 1. This is my Legendre associated Legendre polynomial of order n, that is equal to 0, and degree m, that is equal to 0 also. P00. Now let's go for next. Now n is equal to 1 and m is equal to 0. Let's try this. So this will be P10 of x, and this is 1 minus x square raised to 0 upon 2, then 1 upon 2 raised to 1 into 1 factorial multiplied by d raised to 1 divided by dx raised to 1, and this is also x square minus 1. So get this, now this is raised to 0, so this is going to be simply 1, this particular product. Then 1 upon 2 raised to 1 is 2, 1 factorial is again 1, so we need not go for this calculation. And this is d by dx of x square, so that is going to be twice x minus 1. Okay, minus 1 differential is simply equal to 0, so that is what x square, and getting this differential I'll get this 2 will get cancelled and we'll get simply x. So that's what in this list of P10 of x is equal to simply x. And go for another calculation. Likewise, we can go for several other calculations. N equal to 1 and m is equal to 1 2. So using this Rodriguez formula, we can obtain all the associated Legendre polynomials. So that is P11 of x is equal to 1 minus x square, that raised to now 1 by 2. N is 1, there is 1 by 2, and 1 upon 2 raised to 1, then 1 factorial multiplied by d upon d. Now this is m is 1, n is 1, so this is d square, this is also d square, dx square, and in the bracket x square minus 1 raised to 1. So solving this, I'll get 1 minus x square divided by 1 upon 2, this is for this, and getting this differential, okay, d square upon dx square of this bracket x square minus 1. So getting this differential, I'll get just like here, it is d by dx is twice x, and its differential is simply equal to twice. So 2 will get cancelled and we get 1 minus x square. So this P1 of x is equal to 1 minus x square. So onwards this, the associated Legendre polynomials are different ones. So Legendre associated Legendre polynomial P1100 of x and P10 of x, they are identical to Pnx, that means P0x and P1x, that is normal Legendre polynomial and associated Legendre polynomial. First two members are just same, but third member onwards there starts a difference, and this is what we can calculate it like this. Likewise, we can go for P21, P22, as well as we can go for P31, P30, so then P31, P32, P33, etc. All these components can be obtained, and that is the method with which one can go for this calculation of calculating all these associated Legendre polynomials from the Rodriguez formula. So these are the two methods. From series solution, one can get this associated Legendre polynomials. From Rodriguez formula, also one can get this type of associated Legendre polynomials. And there is another method that is called as the generating function too. Here is also one can go for the generating function, but that is not we are going to discuss here. So these are two things are important for us, and that is what we will go for further. Okay, now let's go from some properties, some important properties from the examination point of view. Properties of associated Legendre polynomials. Associated Legendre polynomials. properties of associated Legendre polynomials. Now what are these properties? You have to prove this property first. Show that this n0 of x is equal to Pn of x. That means order n and degree 0, order n and degree 0 associated Legendre polynomial is nothing but this normal Legendre polynomial. You have to prove this. Okay, proof. Now see this formula, Pnm of x is equal to, we have just now written this formula, 1 minus x square raised to m upon 2 into d raised to m upon dx raised to m of Pn of x. This is the expression. Getting this associated Legendre polynomial from normal or ordinary Legendre polynomial, we have to apply this particular expression. Now therefore I just want m is equal to 0, so put m is equal to 0, and we'll get here it is 1 minus x square raised to 0 upon 2 into d raised to 0 upon dx raised to 0 into Pn of x. Now here 1 minus x square raised to 0 is simply 1, and d raised to 0 upon dx raised to 0 is going to be 1, and therefore simply Pn of x remains there, and that is what we will get. Pn0 of x is equal to Pn of x. Means from any ordinary Legendre polynomial, getting the associated Legendre polynomial of degree 0, n is equal to 0, is just same. So that's what we will get. That is what already we have seen. P1 of 0 of x is equal to P1 of x. Same thing if I go for P2 of 0 of x is equal to, it is also P2 of x. Same is the case, P3 0 of x is also equal to P3 of x. So these are the normal Legendre polynomials. These are the associated Legendre polynomials of degrees 1, 2, 3 and orders 1, 2, 3 and degrees 0, 0, 0. So P1 0 of x is P1 of x, P2 0 of x is also P2 of x, P3 0 of x is equal to P3 of x, and this can be obtained by using the same method which is shown there. So this is our first property. In examination, in some of the question paper which I have just now discussed before starting of this lecture, we will find some of the questions, this type of questions already have been asked in the examination. So for that you must know how to get the associated Legendre polynomial from this ordinary Legendre polynomial. So this expression Pn of nm of x is equal to 1 minus x square raised to m by 2 into d raised to m upon dx raised to m into Pn of x. So this operator must be known. It is to be operated on this Pn of x, and we get associated Legendre polynomials as shown by this calculation. So for every order Legendre polynomial, associated or 0 degree associated Legendre polynomial is just same. That is shown by P0 1 0 of x is equal to P1 of x, P2 0 of x is equal to P2x, and P3 0 of x is equal to also P3x. So that can be tested from this property as shown above. Okay. Then second, number 2, another very important property that one can go for this. Pnm of x is equal to 0 if m is greater than n. That means degree of the associated Legendre polynomial, if it is greater than order of the normal Legendre polynomial, then all such associated Legendre polynomials are found to be simply 0. So let's prove this. On the holiday too, students are not joining on time. बऱ्याच वेळा हे लक्षात येतं की बऱ्याच वेळाने आठवण आल्यानंतर मग आपण लेक्चरला जॉईन होतो, बिकॉज आय हॅव गिवन दिस इन्स्ट्रक्शन yesterday only. Doesn't matter. So let's go for next. We have again write this. Pnm of x is equal to, this is 1 minus x square raised to m by 2, and then it is d raised to m upon dx raised to m of Pn of x. So getting associated Legendre polynomial from Legendre polynomial, normal Legendre polynomial, this is this. Now here Pn of x is a polynomial, is a normal, ordinary, Legendre polynomial. Legendre polynomial of degree n. Okay, now if m is greater than n, then what will happen? Then this d raised to m upon dx raised to m of this Pn of x will be equal to 0. We'll see one such example there. So getting mth differentiation of nth degree Legendre polynomials, this is always going to be 0. Okay, that can be seen from the examples. Okay, that is equal to 0. Okay, for example, if I am supposed to get d raised, that is I am supposed to get this P10 of x. So if I write this expression there, I will write this is 1 minus x square raised to 0 upon 2, sorry, 1 upon 2, 1/2, and here, okay, this now d raised to 1 upon dx raised to 1 of, now see P0 of x. Now what is P0 of x? This is 1 minus x square raised to half, then this is d by dx. P0 of x is simply equal to 1, it's constant, it's a number, and differential of any number is simply equal to 0, so that's where I'll get to be equal to 0. So P01 of x is equal to 0. Same thing you can apply for m is equal to more than n. You'll find that every time this differential is going to be 0, and therefore this, in general, this property Pn raised to m of x is equal to 0 provided m is greater than n. So every time your m must be less than n, or at the most it should be equal to m. M should be equal to n, not more than n. This type of associated Legendre polynomials are not defined. Okay, so that's what we write. Hence, write the result. Hence, this Pn of x is equal to 0 if m is greater than n. So these two properties are also asked sometimes in examination, in the internal examination as well as in the university examination. This property of associated Legendre polynomial may be asked sometimes. Okay, now here also this orthogonality condition is here. I am not going to prove this condition because it's a lengthy derivation. If someone wants how this particular calculation comes, you can go for this. Okay, next, orthogonality. Orthogonality of associated Legendre polynomial. Associated Legendre polynomial. Orthogonality of associated Legendre polynomial. So this expression is given as integral -1 to +1. This is Pn of x into, now this is what I am using here, Pn prime, m prime of x. Okay, the n and n prime are different, m and m prime are also different, into dx, that is equal to twice n plus m divide by, sorry, factorial, divide by twice n plus 1 into n minus m, okay, multiplied by delta m n prime, delta m n prime. Actually this m prime is not there, this is not m prime, this is simply m, and here this delta m n prime is Kronecker delta function, Kronecker delta function, and we know as already from this condition that n and n prime are not same, then that is going to be 0. If n and n prime are same, then we will get this n and n prime. Okay, here n is not equal to n prime, then this delta m n prime is going to be 0. Right hand side of this equation is going to be 0. If n and n prime are same, then we get this result which we have shown there. So this derivation is proof, etc. Everything is given in one of the test standards reference books. Check it once. Okay, I don't think it is necessary from the examination point of view. It's a very lengthy derivation. It requires much in understanding of the mathematics, other concepts of mathematics. But if someone is more interested in getting this right hand side of this orthogonality condition of the property of the associated Legendre differential equation, see any of the standard reference book, you will get proof of all this. Okay, I think this 3-4 page proof is there. If someone is interested, he can go for that type of proofs later on. Now we'll see one more, that is the recurrence relation or formula for associated Legendre function. Recurrence relation for associated Legendre polynomial. POLY, I is not there, polynomial. A recurrence relation for associated Legendre polynomial. Now how to get this? Again, these equations are these particular derivations are little bit difficult as compared to earlier. That is what we have seen in this Legendre or ordinary Legendre polynomials. Here first relation is this recurrence relation. We can prove that this Pn m plus 1 of x is equal to, sorry, it's not equal to, minus, let me scratch this, minus, this is twice mx divided by root of, in the bracket, 1 minus x square, bracket complete, Pn m of x plus n into n plus 1. Okay, this n is inside this type of curly bracket, minus m into m minus 1, this bracket complete there, into Pn m minus 1 of x is equal to 0. So this is Pn m plus 1, this is Pn m of x, and this is Pn m minus 1 of x. Okay, so if it is 0, this is 1 and this is 2. So that's why this is called as 3 terms recurrence relation. 3 terms recurrence relation. 3 terms recurrence relation. If anyone is interested in this, also you can go for that. Okay, proof of that is also available in several of the books. So I don't think you should go for all these proofs, but we'll just mention all some of the properties here. Okay, 1 or 2 properties we'll discuss here. This is first recurrence relation. How to get this recurrence relation is, again, as I said, so refer any standard reference books, you'll get this type of recurrence. Basically use Merit publication books, or use this book by I have one of this such book, that is by yes, Sharma and Gupta, Krishna Prakashan Media Private Limited, UP. This is again North Indian book. Sharma Gupta, Mathematical Methods of Physics, or Mathematical Methods. This book which I am using in the class as a reference book, you can use that book to get this particular thing. But as examination point of view, we are not asked this type of problems there, so need not worry. If someone has interest in getting all this type of recurrence relation, he can check all such type of standard reference book. This is first. Second, you can show that this twice n plus 1 x times Pn m of x is equal to n plus m, that is multiplied by this Pn minus 1 m of x minus in the bracket n minus m plus 1 into Pm n plus 1 of x. So here it is n, there is n minus 1 and this is n plus 1. So you can get P n m of x provided we have a knowledge of P n minus 1 m of x as well as P n plus 1 m of x. So this is also three-term recurrence relation. One can get any of the higher ordered associated Legendre polynomials provided earlier two Legendre polynomials are known. So this is a recurrence relation. This is also can be obtained as I said from this, but you can take this particular from any of the textbook or reference book. This is second. Third is root. Again becomes a bit difficult. Root of in the bracket 1 minus x square P n m of x is equal to 1 upon in the bracket 2n plus 1, and here it is in the bracket P n plus 1 m plus 1 of x minus, this is another associated Legendre polynomial, this is P n minus 1 and m plus 1 x. Okay, there are several others. I think there is no need to go into details of all this. There are several other numerical equations are there that also may be seen there. As I said, we can express this x. Sometimes we use Pn of cos theta. Now how to go from x to cos theta? That type of derivation we'll see here, and that is the last derivation from this particular chapter. That will be do as follows. Okay. So in case of associated Legendre polynomial, this trigonometric series for Pn of x. Trigonometric series for Pn of x. So this sometimes we replace this x by cos theta, and so how to do these things? Okay. Now since we know, okay, we have seen this property, summation over n equal to 0 to infinity. Okay, that is t raised to n into Pn of x is equal to, this is 1 minus twice xt plus t square raised to minus half. This is generating function of Legendre polynomial. We have in the very first lecture of the chapter we have seen this. This is generating function of Legendre polynomial. G of xt is equal to, in the bracket, 1 minus twice xt plus t square raised to minus half. That is called as Legendre, generating function of Legendre polynomial. Expanding this generating function around t is equal to 0, we get the series in t raised to n with constants, with this coefficients Pn of x. So P0x, P1x, P2x, etc. These are called as this Legendre polynomials. We have already seen all these discussions there. Okay. So now replace x by cos theta, substituting x by cos theta. Okay. Everywhere you have to replace x by cos theta. So therefore we'll get summation over n is equal to 0 to infinity. Then it is t raised to n Pn of cos theta is equal to 1 minus twice t into cos theta plus t square raised to minus half. So let's solve this. It gives you, okay, now I am replacing this cos theta exponentially it is given by e raised to I theta minus or plus e raised to minus I theta upon 2, isn't it? So this can be done here. Now this 2 and this 2 will get cancelled, and therefore one will get 1 minus twice t into the bracket e raised to I theta plus e raised to minus I theta. Okay, I can use this bracket here, not this. 1 minus twice t e raised to I theta plus e raised to minus I theta upon 2 plus t square, and this bracket raised to minus half. So simplify further. Simplifying this, you'll get this as equal to, I'm just writing all these things given in textbook. So this is in the bracket 1 minus t into the bracket e raised to I theta plus e raised to minus I theta, this is this particular thing here, plus t square raised to minus half. Again simplify this, I can write this as in the bracket 1 minus t into e raised to I theta, t into e raised to plus I theta, this is taken outside of this bracket. If it is done this way, into 1 minus t times e raised to I theta minus I theta, minus I theta, this bracket, and then this bracket completed, rest, this is bracket in the bracket, rest to minus half. And that's what it can be done. In the first bracket is 1 minus t into e raised to I theta, that raised to minus half, and this also 1 minus t times e raised to minus I theta, that also raised to minus half. Now this is, you have to use an expansion 1 minus x raised to minus half. That expansion you can use for the first series as well as you can use the expansion 1 minus x raised to minus half for the second series. So doing all these expansions and long series are there, you can go all this type of calculations, and I think I should not give it here. Okay, in between things are not needed. So this is long derivations is there, and therefore this Pn of cos theta final series. Okay, you can write series of this, you can write series of this, adjust the terms, and you will get this as 1 into 3 dot 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 up to twice n minus 1 divide by 2 into 4, all the positive coefficients, even coefficient in the denominator, product of that, and all the odd coefficient in the numerator, product of that, there, into 2 into cosine of n theta plus twice n upon twice n minus 1. Okay, all these things I have not done in between steps, so you need not worry about this. 1/2, then 2 into cosine of n minus 2 into theta, 1 minus 2 into theta, that is my first term, plus here also 2n divided by 2n minus 1, and product of this 2n, then twice n minus 2 divided by twice n minus 3. Okay, so lengthy one. Okay, you need not go into details of all these things. Okay, multiplied by 1 into 3 into dot 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 up to okay, all other terms there. So it is multiplied by 1, 2 into 4, and it is to be multiplied by 2 cosine of n minus 4 into theta plus higher order terms. So this is going to be an infinite series. Pm of cos theta is going to be infinite series of cos theta, and that is how, this is what a different thing, that is in quantum mechanics we use basically Pm of cos theta rather than Pn of x. Pn of x is used in mathematics, in quantum mechanics, with the substitution of x is equal to cos theta, we can write Pn of cos theta. That appears to be a very long series as shown here. You need not worry about this series here, how to get this series and all that things that has been covered in several standard books. You need not worry about this, but try to understand this is what this associated Legendre polynomial plays a very vital role or important role in finding out this spherical harmonics. Okay, so this the application of associated Legendre polynomial. Okay, so actually we have already done this, but we'll just repeating these things. Solution of angular solution, that is theta phi solution of Schrodinger equation is given by spherical harmonics. And that is what we have already written this expression, YLM of theta and phi, that is written by this. N is normalization constant. Okay, then it is multiplied by e raised to I m phi, that is phi part solution, multiplied by PLM of cos theta. YLM theta phi is equal to n times e raised to I m phi into PLM cos theta. So that is what, as earlier, this is your associated Legendre polynomial. So my point is that without learning this associated Legendre polynomials, or without knowing that how these polynomials do come, what is the differential equation there, what are actual this associated Legendre polynomials, how to obtain this associated Legendre polynomials from ordinary Legendre polynomials by operating that operator, or using this Roderick's formula, how to obtain all these associated Legendre polynomials. Without that, we will not be able to carry out the mathematical analysis of spherical harmonics, and unless we understand this spherical harmonics, we will not be able to write the wave functions of hydrogen atom, in which orbit it is, and based upon that we can get expression for the different types of orbits, and based upon that in atomic physics we go for configuration 1s2, 2s2, 2p6, etc. This configuration could not be written unless we understand this associated Legendre polynomial. So first part of that, n times e raised to I m phi, is very easy. That is simply an exponential function, but this PLM of cos theta, that is the important part of this YLM theta phi or spherical harmonics. With the help of that, different angular shapes of different types of orbits can be predicted. Then its capacity, that means how many electrons in an orbit can be accommodated, that is also decided. Based upon that, we can go for several other properties of electron in that orbit. For example, its orbital angular momentum, using this operator of that orbital angular momentum operator, quantum mechanical operator, over this spherical harmonics, I can get the value of the orbital angular momentum of that electron in that orbit. Similarly, we can go for this magnetic or angular momentum or of that electron in that orbit, provided we have that operator, and that is to be operated there. That means for an electron in an hydrogen atom, in which orbit it is, all its physical properties can be found out once we know this spherical harmonics. And to understand and to know this spherical harmonics, we must know this associated Legendre polynomial. So origin of associated Legendre polynomial, so that actually start from this Helmholtz equation, that is to be solved in the spherical polar coordinate system. In separating this angular part from this r part equation, we come across there is a numerical constant n into n minus 1, and adjusting this constant in our differential equation as we have started here. This is what the first differential equation which we have seen, that is this associated Legendre differential equation. So try to compare, every time you should go on comparing the normal or the ordinary Legendre differential equation, and so many things about this, right from its solution, then its Roderick's formula, then its generating function, then its all the other properties, recurrence relation, its orthogonality, etc. On the similar grounds, just making this change n into n minus 1 in this equation, associated Legendre differential equation becomes different, and solution of that. Then how to get a solution of associated Legendre differential equation? If I know solution of the Legendre differential equation, by taking this operation, Pn m of x is equal to 1 minus x square raised to m by 2 d raised to m upon dx raised to m into Pn of x, when can get all such associated Legendre polynomials. And there is second method, as I said, Roderick's formula is also available there. You can go for that type of formula. We can find out all such associated Legendre polynomials from that Legendre formula too. Then these are the properties, two important properties. One is related to Pn0 of x is equal to Pn of x, that can be shown by the simple calculation. Then Pn of m of x is equal to 0 provided if this coefficient, this particular n number m is more than n. And I think that is what we can go for in quantum mechanics. We take values of L is equal to n minus 1 up to n minus 1, and for every m we have m values equal to minus L2 plus L. So this restrictions upon these quantum numbers, these restrictions from these conditions, mathematical conditions which we have tested or which we have seen here on this associated Legendre polynomial and all that. So what we learn in atomic and molecular physics, what we learn in quantum mechanics, and what is its basic in mathematics, that can be understood from this type of derivation which we have just now seen. So this is what this associated Legendre polynomials, its properties, its recurrence relation, its orthogonality condition. Then in trigonometric conversion, that means replacing x by cos x and adjusting all the terms, this Pn of x, Pn of x Legendre function Legendre polynomial can be expressed in the trigonometric series again, that is Pn of cos theta. And in quantum mechanics, we are supposed to use this Pn of cos theta in preferably to write all these spherical harmonics. And once we understand these spherical harmonics, we can go for several physical parameters of electron in an hydrogen atom in different orbits, and all the properties, physical chemical properties, can be discussed very nicely provided we have a knowledge of all these spherical harmonics. So here we have finished this spherical harmonics part. We have finished this associated Legendre functions or polynomials, its properties, its parameters, that how to find out this, etc., etc. All these things we have discussed here. So almost each and every topic from this module 3 we have covered, right from this Legendre differential equation. Then we have gone for all of its parameters, like its generating function, how to get this Legendre function, Legendre polynomial from infinite series of getting this power series solution of Legendre differential equation. Then we have seen its generating function, we have seen its Roderick's formula, we have seen several of its properties, recurrence relation, we have seen its orthogonality. Same thing we repeated for Hermite differential equation, starting from Hermite differential equation to its orthogonality also we have seen each and everything. Then we have gone for Legendre differential, Bessel differential equation, its solution, its generating function, then its Roderick's formula, as well as all other parameters, that means its properties. Its orthogonality is not seen there, it's not part of our syllabus. And similarly, same thing we repeated for this Legendre differential equation, its solution, that is Legendre polynomials. All the concepts what we applied or what we discussed in case of Legendre, Hermite and Bessel, same concepts we have discussed in case of this Legendre differential equation as well as Legendre function, Legendre special function. And same thing, that is what, how to get L1, L2, L3, how that is P1, P2, P3, how to get H1, H2, H3, how to get J1, J2, J3 or their properties, how to get L1, L2, L3 from Roderick's formula, from generating function, everything we have repeated one by one for all such functions. So all these then we have exclusively taken 2 lectures on this spherical harmonics. We try to understand the concept of spherical harmonics, and this spherical harmonics I have already put on my YouTube too, or it is available on your LMS too. You can look that particular lecture to understand this concept of spherical harmonics. And then we have discussed today the concept of this associated Legendre differential equation, difference between normal Legendre differential equation and associated Legendre differential equation. Provided if it is known, we can go for all the steps what we followed in case of all remaining 4 special functions, that also can be applied for this associated Legendre polynomials. And its application, as we have seen, is one of the very important. That is, we can write all the spherical harmonics with the help of this associated Legendre polynomials, and that is what ylm of theta pi is equal to n times e raised to im pi into plm of cos theta. And that's how this you will understand. You will require this analysis when we go for quantum mechanics. In quantum mechanics, we will come across this type of relations or derivations either in simple harmonic oscillator, quantum mechanical simple harmonic oscillator, rigid rotator, in hydrogen atom. Everywhere this spherical harmonic plays a very vital role in understanding all the physical concepts as well as properties of the system. So here we have finished this module number 3. Even though today is a holiday, we have taken some extra lecture to complete this. So henceforth I am not needed to take the lectures of this module 3. Maybe in the after 2-3 days we will discuss some numerical questions, not numerical questions but some MCQs, which will be important from the examination point of view related to this module number 3. As I said earlier to you, go for the assignments which I have provided. All the questions that have been asked, entire 5 years question papers, they are to be collected together on this module 3, and that is to be submitted physically online as well on your LMS, as well as physically you have to submit it for your internal score or internal credit. Whatever internal score we are supposed to get, that will be based upon this particular assignments which I have provided there. So this is where we have finished this chapter, module number 3. In the next week onwards, after your examination, we will start this Fourier integral for Fourier algebra or Fourier series and integrals, Laplace transformation, Fourier transform, Fourier integral transform, inverse Fourier transform, and Laplace transform, etc. All these mathematical details or its applications, etc., that will be see in the next week after finish of this internal examination. Okay, so let me stop there and let me take the attendance. Thank you all. Nice for cooperation.